Nerve impulses travel in our bodies as electrical voltage signals. A stimulus received by the neuron cell body initiates a change in the potential difference across the membrane. The resulting action potential travels along the axon to be transferred through a synapse to other neurons or muscle cells. This lab models so-called passive transport, which occurs when a voltage signal is either A, below the action potential threshold level necessary to stimulate active transport via voltage-gated ion channels, or B, where some axons are wrapped in a myelin insulating sheath between the uninsulated nodes of Ranvier. This rapid conduction of the signal from one node to the next, with a refreshing of the signal at each node, is referred to as saltatory conduction. This lab is intended to emphasize two principles. 1. Active transport through the axon membrane via voltage-gated ion channels powered with ATP is necessary to boost nerve signals over distances of more than a few millimeters. Passive transport is inadequate for longer axons. 2. Myelination of axons, wrapping in heavy insulation material, can increase the distance and speed and preserve the quality of nerve signals in many axons. For a great introduction to the concepts used here, explore the highly educational animations found at 7e.biopsychology.com. If a stimulus voltage signal is initiated in the axon at a level below the -50 millivolt threshold to activate an action potential, the passive signal that propagates along the axon dissipates in only a few millimeters from the point of initiation. A reasonable model of the axon is a relatively high resistance cylindrical membrane filled with a conducting axoplasm fluid and conducting extracellular fluid. As a representative circuit, consider a series of axon resistors coupled by leaky membrane resistors to the extracellular fluid conducting wire. A relatively large current may begin where the voltage is applied, but by the time it travels down the line, much of the current is leaked out, and after a few millimeters, only a small current, and therefore small voltage, remains. A plot of voltage versus distance decreases as a decaying exponential with distance from the origin. The characteristic signal decay length, lambda, depends on the square root of the ratio of the membrane resistance to the axon resistance. A larger membrane resistance leads to less current leakage and thus a longer decay length for the signal. The signal also propagates with a finite speed from the stimulus, even as it is degraded in scale and quality. We model the finite speed of the signal in our circuit by placing membrane capacitors in parallel with the membrane resistors. The finite charge-discharge time required for the capacitor-resistor combination delays the propagation of the signal. If the signal propagates a distance lambda in a time given by the RC time constant tau, then the predicted speed of the signal will be distance over time, that is, lambda over tau. Here is the breadboard on which the circuit is assembled. Note that within the wide central strips of the breadboard, the holes are connected in vertical columns, with a large gap in the middle. Along the bottom and top, the rows of holes are connected from end to end. We call these long connected lines buses. This diagram shows where the solderless connections are placed on the breadboard. Vertical columns are connected through the two central regions, and a pair of buses top and bottom. Here's how the first unit of the axon circuit is placed. The axon resistor bridges a span of holes, and at the downstream end is connected to both the membrane capacitor and membrane resistor, which form a parallel combination into the bus at the bottom that represents the extracellular fluid. Make certain that the negative shorter lead of the capacitor ties into the bus. We're using 100 ohm resistors for the axon resistor, 330 ohms for the membrane resistor. The ratio of R membrane to R axon is about 3, and it's not too different from that of a real axon. We are using a 470 microfarad capacitor to give an easily measured speed down the circuit. Copy and paste the basic unit down the length of the axon circuit. Do this for at least 4 units. A signal generator will be attached at the input end of our circuit, and voltage probes will be placed at each of the first 3 stages down the axon circuit. The signal is provided by the Pasco unit's output terminals. The stimulus signal is attached at the input end of the axon circuit. Here are the placements of each voltage sensor: input A, input B, and input C. In Data Studio, after indicating that voltage sensors will be in use in all 3 input channels, set the sample rate at 1000 Hz. Click on the virtual output terminal and set the signal voltage to a 1 volt amplitude with a ramp down wave, a frequency of 1/2 Hz, and manually toggled on and off. Drop and drag the graph icon onto the output voltage and inputs A, B, and C in turn so that all 3 plots are on the same time axis. Initiate recordings with the following sequence. 1. Click Start. 2. Quickly turn the signal on and wait a couple of seconds. 3. Turn the signal off, and finally, 4. Stop recording. You should see a grouping of signal bursts. Any resemblance to an action potential is unintended. This is just meant to be a sharp, easily tracked signal. Use the XY tool to record the times and voltages for each pulse in the chain. I recommend recording the location in each spike where the voltage first takes on its maximum value. To translate each unit along the axon circuit into a distance in centimeters or meters, measure the length of a resistor. Then the distance down the circuit will be the location number n times the length of a resistor. Plot natural log of the voltage peaks versus distance x. The decaying exponential becomes linear on a log plot with a slope equal to the negative inverse of the signal decay distance lambda. Also plot position versus time to get the speed of conduction of the signal. Compare the speed with the lambda over the RC time. Myelin wrap is an insulating sheath that greatly enhances the resistance of the membrane. Our circuit model for a myelin-wrapped axon length involves removal of membrane resistances altogether until the end of the myelin tunnel is reached. This assumes an exaggerated infinite membrane resistance through the myelin. The voltage signals now travel down the circuit at the speed of light. Too fast to measure with these tools. They remain distinct and drop linearly with distance rather than the rapid exponential decay of the unmyelinated axon circuit. A plot of voltage versus position shows the linearity of this simple voltage divider circuit. Finally, I note with genuine awe for our Creator God the complexity of the simplest circuit that might be used to model active transport of an action potential. Here, the sodium-potassium ion pumps maintain EMFs across the membrane, with a membrane voltage modified with adjustable resistors representing voltage-gated channels. Time and resources prevent our construction of this rather complicated circuit.